Thanks. Yeah, so I want to try to talk a little bit about how one proves the classification theorem, and the proof I'm going to follow is a recent one, not the original proof, but looking from joint work with José Carrión, Jamie Gabe, Aaron Tikuisis, and Stuart White. I'm going to make these simplifying assumptions. As I mentioned in my first talk, that I'm going to assume the algebras are Q stable instead of Z stable, and that they all have unique trace. That special case is sort of implicitly in an earlier paper of mine, but a lot of what I'm going to say is still going to be newer stuff. There's various things I did in ad hoc ways that we can now have more systematic ways of proving. But okay, before I do that, though, I do want to say something about what was done classically. And the UHF stable unique trace setting, if you assume a strong quasidiagonality condition, really goes back to about 2005 or so. The quasidiagonality and to finite decomposition ring came much later, but so say the classification assumptions and in this Q stable unique trace setting, A is what's called tracially approximately finite dimensional. So it's a tracially AF C star algebra, meaning that for any finite subset of A and for any epsilon positive. So in some sense, locally, A will look finite dimensional up to some tracial error. So this finite set is almost contained in a certain subalgebra of A, which has this form, where if that, F is some finite dimensional C star algebra. And if this decomposition is with respect to some projection P and 1 minus P, almost commuting with F, which is why I get to put the zeros there, almost commuting with the finite set. I want to know that projection has large trace. This is why I drew the 1-1 corner so much bigger. So up to this 2 norm small, you have this approximate direct sum decomposition of A, so that one summand you have uniform approximations by finite dimensional subalgebras, and the other subband is somehow tracially negligible. Right. That's somehow enough to, we have a very good understanding of maps out of finite dimensional algebras in terms of their K0 group. And you work to show somehow that small corner doesn't get in the way too much. So this has been the real strategy behind the theorem since probably about 2000 or so, to force some kind of tracial approximation on the algebra, then classify the tracial approximate things. If there was several traces, what ends up happening is you need, instead of finite dimensional, you need something like C of 0,1 tensor finite dimensional, or slightly more than that. And when you're not UHF stable, there's an elaborate series of reductions to the UHF stable case. But okay. That's so. I mean, the new approach here. Why I want to say this is that our approach comes very much in hindsight. It's somehow after it was. Some of the final pieces of the theorem were actually obtaining tracial approximations in general. And somehow the way one obtained them shed a lot of light on what was happening and suggested sort of a new way of approaching this. And to say here, make direct use of hyperfiniteness of the von Neumann algebra completions of A with respect to the traces. Let's write it that way, which is just R. I mean, the way you actually get tracial approximations, there's a lot to it, but in the end, you actually are taking finite dimensional approximations of the von Neumann algebra completion and somehow turning them into this. I mean, you can think of it like an Egorov type theorem if you like, that you have finite dimensional approximations in 2 norm. You're replacing 2 norm with the infinity norm modulo some set of small measure. Yeah, somehow it turned out to be possible you could bypass that step and just work directly with the finite dimensional approximations of the von Neumann algebra. Right. Okay, I'll say more about how that's done. But so it's the classification theorem in the special case I'm considering will follow from, as I suggested in the last lecture, a classification of morphisms result. So if you have a separable, unital, nuclear, UCT, and with a distinguished trace, which is faithful. So A could have many traces, but it has at least one faithful one, and I'm going to just fix that one once and for all. And B is going to be simple, unital, exact, Q-stable with unique trace. Trace on A is not necessarily unique, yeah. So it's A and B as in the classification theorem satisfy both the conditions of A and B here under my working assumption that they're all Q-stable with unique trace. But so then the unital trace preserving embeddings are classified by the K-theory. So in the same sense I defined last time that you have these uniqueness and existence theorems, say if B and psi from A to B are unital homomorphisms, which are trace preserving, in the sense that they carry the unique trace on B to the prescribed trace on A, and they agree on K-theory. Let's write it this way. If they agree on K-theory, then they're approximately unitarily equivalent. And the existence portion is about the same. If you have a K0 map, K0 of A to K0 of B, which preserves the unit. Oh, I want 2 maps, one on K0, one on K0, one on K1. So the map on K0 takes the class of the unit to the class of the unit, and it preserves the trace. The trace on A will induce a states on K0 of A by just evaluating at a trace on projections. Tau B alpha naught equals tau A. Maybe I'll put hats on these for the induced maps on K0. Then there's a unital trace preserving phi, which realizes this.
So Chris, could I pull out? There's a question in the Zoom chat about why the von Neumann closure is the finite to one factor. Does that have anything to do with Q stability, or are there some other?
Oh, not coming from Q stability. It's so it's nuclearity will give you the von Neumann algebra completion, injective, and then hyperfinite. Unique trace is what's giving you a factor as opposed to some other tracial von Neumann algebra. Oh, and then I guess you do need something. I guess Q stability forces A to be infinite dimensional, which stops it from being Mn. Yeah, but a nuclear unique trace, when you complete it, you always get either Mn or R. And yeah, Q stability will force it to be infinite dimensional. But yeah, nothing close to the full strength of Q stability. In this one, yeah. Maybe I should have called that a B to match what I wrote just after, but yeah. Yeah, here. A, let's say, separable, nuclear, unique trace. And I guess what I really want is the von Neumann algebra completion infinite dimensional. I guess A being infinite dimensional itself isn't enough because unless you have simplicity or something. Good, but yeah. Right. Okay. So what you get out of this classification of morphism result from here, like I did last time, you can apply this to build maps from A to B and from B back to A. And then using the existence, then use the uniqueness to compare the compositions to the identity maps. And you'll get back to the isomorphism in the theorem. Okay. So, go on. I should mention this is not, if you replace Q stability with Z stability, this is not true as stated. There are actual extra K-theoretic assumptions, which I don't want to say a whole lot about here. But I want to mention a consequence of this. Or before that, maybe. The theorem, the embedding theorem applies far more than just in the study of the classification theorem because you don't have any simplicity condition. That this A could be C of X. And you classify maps for commutative algebras into AF algebra, into such algebras B, which is actually known earlier by Wash and Lin in the C of X case. Or A could be a group C star algebra when G is amenable. And what's that, countable discrete? The trace being the usual trace in the left regular representation. There's non-classifiable algebras, which this will apply to. Yeah. Yeah, the embedding condition is automatic. Yeah, it's what was that? If you had a positive element in the kernel, it would have to have trace 0 by the trace preserving condition. And then it has to be 0 by faithfulness of the trace. Yeah. So the embedding is actually forced because you preserve this faithful trace. Yeah. So the consequence of this, if A is separable, nuclear, UCT with faithful trace. So there's this long-standing problem of Blackadar and Kirchberg asking if every separable nuclear stably finite C star algebra embeds into an AF algebra. This faithful trace condition you can think of as a very strong form of stable finiteness. So under that strong finiteness and the universal coefficient theorem, this Blackadar-Kirchberg problem has a positive answer. In fact, you can even arrange it to be a simple AF algebra. So a very large class of C star algebras, including all amenable group algebras, end up embedding into AF algebras. Right. And I want to, actually, yeah. Yes. Yep, C of X and yeah, group algebras for amenable groups. Yeah, A can be any of these. Pretty much putting C of X into an AF algebra is actually not difficult. You write X as a quotient of the Cantor set and then dualize. The group algebra case was also known before this. You ended up cross product constructions embeds this into a classifiable C star algebra and then use classification to put an inductive limit structure on that. There are various cross product examples you can take as well. Yeah. Yep. So, yeah, I'll explain how to get the corollary from the theorem before I go on with the theorem. So you can assume A is unital just by adding a unit. A embeds into its unitization, and the unitization will have all the same properties. So what the classification theorem is giving you is it's enough to find some sort of AF embedding on K0. If you can find the AF algebra B and with all the properties above and this trace preserving map on K0, then it necessarily came from a homomorphism. So it's a problem with building this AF algebra in such a way that you can construct this K0 map. And here's the game. You take, well, all right. You can take the range of the trace on K0 of A. That's some subgroup of the real numbers, countable subgroup. I'll take its rational span and call that G. So one thing I didn't mention much earlier, the range of the Elliott invariance is very well understood. If anything given any K0 group, any K3 groups in any trace simplex, you can find a classifiable algebra with those properties. And you can read a lot of structural properties off of the Elliott invariance. So it turns out here, a very special case of that, countable subgroups of the real numbers are always K0 group of a simple AF algebra. Well, it's a special case of the Efros-Handelman-Shen theorem, if you've seen that. There's a simple unital AF algebra B with unique trace. And well, K0 of B is isomorphic to G, and the isomorphism given by the trace. So that's a result of Elliott shortly before the general Efros-Handelman-Shen theorem. And what you end up doing is you show G is a direct limit of things like Z to the n's with their pointwise order structure. So once you decompose G as a direct limit of K0 of finite dimensional algebras, then you just lift all those K0, you lift the inductive limit structure back to the C star algebra level and end up with the AF algebra with the prescribed K0. Okay. Also, I'm close to the B I need. It's simple, unital. AF algebras will be exact. It has unique trace. The Q stability is the reason for the span there. K0 of B as a group is K0 of B tensor of the rationals because it's a rational vector space. And tensoring with Q on the K0 level corresponds to tensoring with Q on the C star level. But now B and B tensor Q are both AF algebras. They have the same K0 group. So B is Q stable. You have to be a little bit careful with the order on K0 and this isomorphism, but the order on this thing does turn out to be what you'd expect here. It's the cone generated by positive elements in K0B tends to positive rationals. Right. Then, so that's the B I'm going to apply the existence to. I also need this map alpha. Alpha naught is, well, just built out of these traces. You take the trace on A, that maps you into G. The trace inverse of B maps you into back to K0 of B. So that's my map on K0. The map on K1, you don't have a choice because AF algebras have trivial K1. It's just the zero map. And then you apply, as I was saying before, apply existence to that. Alpha's in, you have this map from K theory to A to K theory B, preserving unit and trace. It's necessarily came from embedding A into B. Okay. Right. So let's say something about where this is coming from, and well, especially this corollary always, the proof always seems a bit backwards, that you're trying to show A embeds into B. You don't have, you somehow classify all embeddings and then say a fortiori at least one existed in the first place. And it's always, you know, somehow seems wrong that you don't know any exist, but can write them all down. What's happening there is there's another intertwining argument hiding behind this. So, as I say, by another intertwining argument, which has been used for at least 20 some years now. Instead of dealing with actual homomorphisms, it's enough to classify approximate embeddings. In quotes here. So instead of, yeah, so you'd have a whole sequence of maps, phi n from A to B. Let's assume they're unital completely positive, but you could relax that to some extent. And as n goes to infinity, they behave like homomorphisms. So they preserve the product in the limit. And well, in my context here, I'm going to want them to preserve the trace in the limit. In other contexts, you might replace that with their isometric in the limit or something of that nature, but right. So you get the same sort of, you'll get the same kind of statement. There will be an existence result or uniqueness result if you have two such things, and their behavior on K theory is sort of asymptotically the same. Then there's a unitary conjugating the phi n's, a sequence of unitaries conjugating the phi n's close to the psi n's as n goes to infinity. And existence, if you have well, map on K-theory, there's some phi n's which asymptotically implement it. Right. So what happens is you're asking for, right, is approximate uniqueness that way. The approximate form of your uniqueness theorem is just harder than the actual uniqueness theorem because there's more approximate morphisms than actual morphisms. So you're trying to prove uniqueness for a bigger set of things. That's going to imply the uniqueness for actual morphisms automatically. The payoff, though, is you're asking now for a much weaker existence theorem. You don't need an actual homomorphism, just some sort of approximate homomorphism. But it turns out you can, here's the intertwining argument part of it. You can use the weak form of existence and the strong form of uniqueness against each other to strengthen the existence result. So roughly find, given your approximate morphisms phi n with correct K-theoretic behavior, you show after passing to a subsequence and conjugating by unitaries, you can make it Cauchy. So let's say add UK of phi sub n sub k. Right. So if your approximate morphism is Cauchy, then you take the limit, and that limit point is actually a homomorphism. But if you just build these maps all over the place, that you can use the uniqueness to show passing to a subsequence and conjugating by unitaries will force them to be Cauchy, or you can force this to be Cauchy, and then the limit is what you get in the existence. Right. So yeah, what makes this version easier is building the approximate morphisms is well, easier than building actual homomorphisms, of course, but it turns out these approximate morphisms always exist. This is a quasidiagonality theorem. And the way I stated it's going to look nothing like quasidiagonality, but so this Tikuisis-Venter quasidiagonality theorem was one of the last big pieces of the classification. What it gives you is they're under the same conditions on A. There exist approximate embeddings. From A into the UHF algebra Q. So you have now approximate embeddings to work with. And also for B is above, you can put Q into Q tensor B by just sticking in the second coordinate. And by my Q stability, that's B. So the quasidiagonality gives you approximate embeddings A into B to start with. There's no information on the K theory of, well, the proof is certainly not constructive, but it's also gives you no K theoretic data. You can't build these maps with prescribed K theory. And I don't think there's a way around it, but even the existence portion, you actually start with knowing there's at least one map and then afterwards work to perturb the K theory somehow. That you can't somehow build the K theoretic map in one go or get the K theoretic information in one go. Okay. Right. So how does one prove this approximate classification is what it comes down to. I'm going to restate this once more. There's approximate morphisms can be somewhat working with these approximate morphisms is somewhat delicate. Especially when you start talking about K-theoretic things, a UCT map just doesn't induce a map on K-theory. But the approximately multiplicative maps give you some kind of approximate morphism on K-theory, which is only approximately well-defined. This has all been worked out on how to deal with this, but it gets rather messy. Okay. So one more restatement of the theorem. I'm going to replace the approximate morphisms with actual morphisms at the expense of making the codomain much bigger. This is a standard tool in both C-star algebras and von Neumann algebras, and probably elsewhere. So you pass to approximate morphisms A to B will correspond to morphisms into an ultra power of B. So let B omega be all bounded sequences in B, modulo all such sequences. That in norm converge to 0. Along some free ultrafilter omega. If you don't want to think about ultrafilters, just think of it as the usual limit. It won't really change a whole lot. I mean, both things won't be true as I state them, but you'll still get the same point out of it. So an approximate morphism phi from A into, well, phi n from A to B will induce a morphism, a genuine morphism from A to B omega by sending your A to just a sequence phi1 of A, phi2 of A, and so on. So the norm of a sequence B in here is that limit of norm Bn. But the fact that the maps are multiplicative then goes to infinity means when you mod out by null sequences, they're actual homomorphisms. It'll go from approximate trace preserving to actually trace preserving. So what you get out of that is it's enough to classify morphisms, let's say trace preserving embeddings, unital like before. So for when A and B are in the classification of embeddings, it'll be the same statement, but in uniqueness and existence, both the maps go into looking at maps from A to B omega, and K theory of A to K theory of B omega. Just replace B omega with B everywhere, or B with B omega everywhere. If you can do that, then you can run this approximate intertwining argument to get back to the theorem as I stated it. There's a general form of this too. It's the hypotheses don't, outside of separability of A, the hypotheses really don't play any role in this reduction. So in the terminology I was using last week, if you have a functor F that classifies morphisms from A to B omega, then it also classifies morphisms from A to B. There's just some general nonsense that gets you there. You need some slight conditions on the functor, but they're always true in practice. Okay. Right. Okay, so this is what we're actually going to talk about, how to describe embeddings into the ultra power of B. And so, there's a couple there's one major benefit of this, which is usually what's part of why ultra powers are used a lot. You can vary all the epsilons in the proof inside of this ultra power, like we did here, turning approximate morphisms into actual ones and not having to deal with things like K-theory of approximate morphisms. There's a more surprising advantage to using this. The B omega has, B is simple. B omega actually turns out to have a fairly complicated ideal structure. There's sort of these approximate ideals in B that become actual ideals in the ultra power in some sense. But turns out it contains a von Neumann algebra quotient. You think of C-star algebras usually as being somehow much smaller than von Neumann algebras. But when you pass this ultra power level, you can actually map the C-star algebra quotients onto a von Neumann algebra. And it's the structure of that quotient that's really going to take advantage of. It's not just any von Neumann algebra either. It's so if I'll write M for this von Neumann algebra completion of B with respect to the trace. So the strong closure of B in its GNS representation. So this, because of the uniqueness of the trace, it's going to be a fact. This completion is going to be a factor. And if B is, say, infinite dimensional because it's Q stable, so it can't be a finite, so it has to be a 2-1 factor. Right. Containing, and B is contained in there as a dense subalgebra. And I'm also, instead of M, M's not actually going to be a quotient. It's something closely related. It'll be the ultra power of M with a different norm. So this L infinity M is all bounded sequences in M modulo the sequences that go to 0, except the operator norm will replace with a 2 norm here. There's now 2 different ultra powers floating around. There's the C-star algebra ultra power where you quotient by operator norm null sequences. I use a lower omega for that. And the 2 norm ultra power where you quotient by, or von Neumann ultra power where you quotient by 2 norm null or strongly null sequences. I'll put use an upper omega for that just to distinguish them. I don't know when this, the lower omega and upper omega has become fairly standard in this realm of C-star algebra theory. It seems to work reasonably well, but I don't know where it actually came from. So lower omega is always C-star algebra, upper omega, von Neumann algebra. There'll also always be B and M, so I won't be switching back and forth. But okay. Maybe it's called a fact. So the inclusion will induce a surjection. Q from the norm ultra power of B to the tracial ultra power of its completion. So that's my, this is again some sort of some von Neumann algebra theory here. It's not actually an obvious statement, but a tracial ultra power or von Neumann ultra power of a 2-1 factor is still a 2-1 factor. That actually takes some work, but yeah. Yeah, I'm choosing the same ultra filter. I don't know if you need to, but you can. Yeah, it's the same one. Yeah. Yeah, I never think about what happens as you change ultra filters. I mean, seriously though, it should be pointed out all of this is independent of which ultra filter you choose. The question of whether the ultra powers are isomorphic as you vary omega is independent of the usual axioms of set theory. But the problems you actually care about usually don't depend on omega, because we're only ever interested in, it's because we're usually only care about separable subalgebras of these things. And it turns out, yeah, unless you're a set theorist, the question you're asking is probably independent of omega, of the choice of ultra filter.
So Chris, we have a question in the chat saying, is this related to one of Hadwin's theorems, saying that tracial ultra power of C-star algebra is a von Neumann algebra, generalizing Sakai? Is this something you know about?
So what was the Hadwin's theorem? Was this, well, I think he had like the ultra powers under continuum hypothesis, the ultra power doesn't depend on the ultra filter or something. Or is that?
Alan, if you want to step in and ask your quick comment.
Can you hear me? Hello?
Yeah, I think that was Hadwin and
Okay.
Hadwin and someone else maybe.
Alan says that we can continue and he'll ask the question again at the end.
Okay, sure. Yeah. Yeah, but for me, I'm going to fix one ultra filter and never change it. The thing you want to prove at the end is maps from A to B. So you're going to get intertwine the ultra filter out of it anyway at the end. Okay. So I do want to prove this factor out here that the inclusion B into M induces a surjective map on the ultra filters. So if, well, fix B in the codomain, and let's assume it has norm at most 1. You can always do by scaling. Well, then any B, so B's, this M omega is a quotient of bounded sequences, so I can represent B by some bounded sequence. M, all with norm 1. This is operator norm. Yeah, they should have been careful. When I say bounded here, I do mean operator norm bounded, but 2 norm null sequences. Yeah. Thanks. Yeah, I'll finish with this and so you have this bounded sequence here. So by Kaplansky's density theorem, there's a sequence in D still bounded below 1 over n. So the unit ball of B is strongly dense in the unit ball of its von Neumann algebra completion. In unbounded sets, the two norm agrees with the strong, induces a strong operator topology. So this comes from Kaplansky's density theorem. And then the Bn prime is a bounded sequence that lifts B, because when you pass the quotient, they have the two norm distance between them is 0. Okay, so I'll just say couple more things. The existence of this quotient map is what's going to, in some sense, drive this. I mean, I guess probably started around 10 years ago or so with Matui and Sato's work, where they found ways of taking properties of the von Neumann algebra and lifting them to properties of the C-star, of the dense C-star algebra along this quotient map. I mean, they did it to lift McDuff's property to C stability under various conditions, including like simple nuclear unique trace and I guess comparison. But somehow it's that lifting problem. We're going to use the von Neumann algebra classification here and try to lift it back along this quotient map modulo K-theoretic obstructions. What I'll talk about more on the last talk is the magic turns out to be that the kernel of this map is very large, but it actually has some reasonable structure. It inherits a lot of properties from B, and you can prove just enough regularity results about the kernel to allow yourself to use extension theoretic results to lift properties along that quotient. But, okay, I'll stop with that for today. Thank you.